Welcome to MS 100 lessons, and in today's lesson we'll be looking at chemical reactions for grade 11 and grade 12. So the outcomes for this lesson is to understand how chemical reactions occur, and the second outcome is that you have to understand the conditions for a reaction to occur. So to explain the concepts that you need to understand in this topic, I will utilize an example. So let's say you have two reactants, okay? You have reactant A and you have reactant B. So the aim is to combine reactant A and reactant B so that you can get a specific product. But before you get that product, there must be a condition. There must be a condition that is met before you can get those products. And the main outcome for this lesson is to explain the conditions for a chemical reaction to occur. So now, say you have particles of reactant A, okay? So I'm just going to use yellow for illustration purposes. So reactant A is yellow, then it means you have molecules or particles of reactant A. Okay, so you have 4 particles there. So let's say that those are molecules for reactant A. And then you have molecules for reactant B. Okay. And then now you have a container where the reaction is going to take place. Okay. So now you take these particles of A, you put them inside that container. Okay. So it means in terms of illustration purposes, you'd have something like that. There is a molecule of A, another molecule of A, and then the last molecule of A. We have 4 molecules of A. Okay. So now we want to understand what actually happens in this container. So let's say I put reactant A in that container, and then after that I close that container. Okay. So let's understand what's happening inside that container. So number one, these particles of A, or these molecules of A, they are moving. And to be specific, these particles are constantly moving. So there's never a time whereby they will stop inside this container. So they are constantly moving inside that container. Okay. So now, if a molecule is moving, or if a particle is moving, or any object for that matter, if it is moving, then we can say that it has kinetic energy. So that is point number one that we have to understand. Inside that container, those particles are moving. Therefore, these particles have what we call kinetic energy. And number two, we have to describe the motion of these particles, because we said they are moving, right? So let us describe the motion of these particles. So these particles, they are moving constantly in a straight line. Okay. So these particles, they move in a straight line. So what does this mean? It means that, for example, if this molecule is moving in that direction, this molecule will move in that direction up until it collides with the wall of the container. Okay, so in other words, this particle, it cannot move in a curve like that to reach that point. Okay, it moves in a straight line. So even this one, if it's moving towards the container, it's gonna move in a straight line like that. So it cannot curve. It does not have a curly movement. So these particles are always moving in a straight line. Okay, so now we understand that these particles of A, they're constantly moving, and if they're moving, they have what we call kinetic energy. And number two, these particles are constantly moving in a straight line. Okay, and then number three, in terms of the movement, these particles, they move randomly. And what does that mean? It means that these particles, they cannot choose a specific direction to go to or to face, right? So for example, this particle cannot choose to go up and this one to go up and then this one to go up like that. They cannot choose which specific direction to go, but however, they move randomly. So this particle can be moving in that direction, this particle can be moving in that direction, as long as it's moving in a straight line, right? That can be moving in that direction and that can be moving in that direction. So they move randomly inside that container. Okay, so they move randomly, and now as they are moving, for example, this particle, if it's moving in that direction, this particle is going to move in that direction up until it collides with the wall of that container, right? And when it collides with the wall of that container, it will change direction. It might change direction to that direction. Same applies to these other molecules. If this molecule is moving in this direction, it might move in that direction, and then it might collide with the wall, and then it might change direction, right? And also, if this molecule was moving in that direction, okay, and then this was moving also in that direction, and then maybe they reach this point at the same time, that particle and that particle will collide. Okay, and if this particle up here, it's moving in that direction, then it will collide with the wall. So we can see that whenever they collide, there's a possibility that it can change direction, right? They do move in a straight line, but however, they can collide with the walls and then change direction, or they can collide with each other and change direction, right? So that is another point that you have to note. They collide with the walls of the container, or they can also collide with each other. All right. So now we understand that these particles, they're constantly moving. That's number one. And they're moving in a straight line. They're moving randomly, and they can collide with the walls of the container, or they can collide with each other. Okay. So now, remember, we are trying to form a reaction here. We are trying to combine A and B for us to get a specific product. Okay, or maybe C, if C is our product. All right, so now we took A and then we put it in a container. So we only have A in this case. We only have A. So it means A will be moving randomly in this container. They will be moving in a straight line. They will be colliding with each other, or they will be colliding with the walls. They will be changing direction due to that collision and everything, right? But no reaction is gonna occur. And reason being, there is only particles for A, okay? we do not have particles for B in this container yet. Okay, so now we were just explaining the movement of how does this particle move in that container. All right, so now we open that container. When we open this container, we insert these particles of B inside that container, right? So we'd have that particle of B, or that molecule of B, that molecule of B, and the last molecule of B. There are 3 molecules there for B. And then we close this container. All right, so in terms of movement, the same theory applies. The same theory applies. The particles of B, they're constantly moving inside that container, right? And they move in a straight line. Still applies. And they move randomly, and they will collide with each other, or they will collide with the walls of the container. But in terms of collisions now, there is a possibility that particles of A collide with particles of B. So now it's no longer particles of A colliding with each other, or particles of B colliding with each other, and also these particles colliding with the walls of the container. Now it is possible that they collide with each other. So in terms of labeling, if I can label that is part A, I mean particle A, particle A, particle A, right? And then we have particle B, then particle B. So now A and B can collide, okay? And if you see, that is where our reaction has to come from. For our reaction to occur, actually, number one, this is part of the conditions, right? Number one, these particles of A and particles of B, they must collide. So it means somewhere in this, inside this container, A and B must collide. All right, so let's go back to the theoretical part up here. We are saying we want to form a chemical reaction, right? But now a chemical reaction just not just occur. So we firstly have to understand how does a reaction occur actually. And we have explained some of the concept that inside that container, these particles are constantly moving, they're randomly moving, they're moving in a straight line, and those particles are colliding with each other, they're colliding with the walls. And those particles, they have what we call kinetic energy, right? So now, if we want to form a reaction, okay, we first have to check whether it's possible. Is this reaction possible? Okay, that is number one. And I will outline how to actually check whether a reaction is possible. So is this reaction possible? Okay, so we are taking particles of A, we are combining them with particles of B. Is it possible that A can react with B, right? And then if the answer is yes, then we can actually continue to say, how fast is the reaction occurring? So there's actually 2 parts in a chemical reaction. You check whether it's possible, and that's what we call thermodynamics. If it's possible, then we check how fast is the reaction occurring. Then that is what we call rates of reactions, or kinetics of the reaction. So now let's get back to the reaction. We are combining A and B, right? Is this reaction possible? Now we have to check 2 conditions that must be met before a reaction can occur, right? So number one, this reaction, which is A plus B, it has a condition in terms of energy, okay? And this energy, we call it activation energy. Okay, so now let's say the activation energy of this reaction A and B is equal to 10 joules. Now, what is activation energy? This is the minimum amount of energy required for a reaction to occur, right? So it means if you do not have this activation energy, or you do not reach this activation energy, then it means your reaction will not occur, right? So now let us link this to our diagram here. So we said if you put your particles inside a container, they have what we call kinetic energy, right? And then now, if they have kinetic energy, it is mentioned that they are constantly moving. So now let us give these particles kinetic energies. So let's say the kinetic energy of this particle is 8 joules, right? And then this one 10 joules. So we're giving them random numbers here. Then 15 joules, 4 joules, 6 joules, 25 joules, and then 11 joules. So this is the kinetic energy of each particle. So now the condition says this kinetic energy of these particles, okay, it must be at least equal to the activation energy of the reaction. It must be at least equal to, or it can be greater than. So meaning that if you want to check which particles can participate in the reaction, you check their kinetic energy and then you compare to the activation energy of that reaction. So what we are saying is particles that have kinetic energy which is greater than or equals to your activation energy. So it means particles that have 10 and above, these particles would participate in the reaction. Okay, so let us go to our container here, and then we check that condition. That is condition number 1 actually. So let me just note it down here, that the conditions for a reaction to occur. So condition number 1 is that the kinetic energy of those particles, okay, they must be greater than or equals to your activation energy, and your activation energy is the minimum amount of energy required for a reaction to occur. So it means if that minimum energy is not met, then the reaction will not occur. Okay, so activation energy is the minimum amount of energy required for a reaction to occur. So let us go back to our container, and then we check which particles will participate in the reaction. Okay, so number 1, if maybe all these particles had kinetic energy which was lower than 10, then the reaction would not be possible at all. Okay, but we see that some of the particles here may have 10 or greater, meaning that the reaction is possible. Okay, or it can be possible. So let us mark the particles that will participate in the reaction, or that can participate in the reaction. So let us start with this one. It has kinetic energy of 8. Okay, and remember the activation energy, we said it should be, activation energy is 10 joules. Okay, so let us mark them and then see if it's possible. So this one, it cannot take part because the kinetic energy is less than the activation energy, right? So this one, it's a no for this one. And then this particle B, it has 10, right? And the required is 10, so this will take part of the reaction, and then this particle A has 15, which is greater than 10. Therefore, this will take part in the reaction. And then we have 4 joules. So this one, it's less than 10. So this one, it will not take part in the reaction. Okay. So maybe for simplicity, we can mark them with an orange color to say that will not take part, that will not take part. Okay. And then this one, it has 6 and the required is 10, so this one will not take part in the reaction. Okay. And then we have this particle, which is 11 joules, and the required is 10, which is this one will take part in the reaction. Okay. So it means this one is part of the reaction. And then we have particle B with 25 joules and the required is 10, meaning this one will take part in the reaction. So we can see now that we do have some particles of B that have kinetic energy which is greater than or equals to activation energy, or that can participate in the reaction according to the condition, right? So we have 2 particles here. And then for A, we have this particle here, which is 1, and we have this particle here, which is 2. So we also have 2 particles for A that can take part in the reaction. So we do have particles of A, we do have particles of B that can take part in the reaction. So now, in this case, the reaction is possible. It has passed the first condition, okay? So now the second condition for this reaction to occur, these particles, they must be in contact with each other. So meaning that they must collide with each other, okay? So now let us look at the particles that can take part in the reaction. So it's this particle B, that particle for A, particle B, and then that particle for A. So for this reaction to occur, remember these particles are moving randomly inside here, right? And they are constantly moving. For this reaction to occur, particle of A, it must collide with particle of B. And when they collide, remember, when they collide, the kinetic energy must be greater than or equals to your activation energy. So number 2 is that they must collide, right? But when they collide, they must collide with the correct orientation in terms of the facing of those molecules. They must collide with the correct orientation. So number 1 is that they must collide, okay? But they must collide with the correct orientation. All right, so sometimes I normally explain with an example to say that, let's say this is particle A, and then this is particle B, okay? So if this particle A has to join with this particle B, they have to, this particle A must collide with the correct orientation, right? So for example, if this is particle A and this is particle B, they must collide with the correct orientation, right? So that is how we explain orientation. So it's just the facing of those molecules, the facing of these molecules. So it might happen that this particle and this particle, they have to collide through that molecule of A and that molecule of B, and not that molecule with that molecule, right? So the orientation is very important because it's part of the condition. So there are 2 conditions that must be met for a reaction to occur. The first one is that the kinetic energy of those particles, because we said these particles are constantly moving, the kinetic energy, it must be greater than or equals to your activation energy, okay? And then the second part is that they must collide with the correct orientation. So now one may ask, is it possible for these particles that we have marked out here, is it possible for them to take part in the reaction? And the answer is yes, but however, we would have to do something so that these particles, for example, this particle can change from not participating in the reaction to participating in a reaction, right? Something must be done, and that is what we'll be explaining in the next lessons. But so far, for a reaction to occur, these particles must collide with an energy which is sufficient, with an energy that is greater than or equals to your activation energy. That is point number one, or condition number one. And number two, they must collide with the correct orientation. So now we have understood what happens in terms of the movement inside a container, right? And that movement, or that explanation of movement, is actually a theory, right? It helps us explain what happens inside a container when a chemical reaction is occurring. So that is the kinetic molecular theory. So it's kinetic because there is movement, right? And it talks about molecules. It helps us explain what is happening in that container. It says the particles are constantly moving, and as they are moving, they have kinetic energy, right? And they move in a straight line. They move randomly so, and they collide with the walls of the container, and they also collide with each other. While that is happening, or while that is occurring, the movement and collision and everything, if you want a reaction to occur, number one, your kinetic energy must be greater than or equals to your activation energy, which is the minimum amount of energy required, right, for a reaction to occur. And number two, they must collide with the correct orientation. So we have fulfilled the outcomes for this lesson. Now we understand how a reaction occurs, right? Particles are constantly moving inside a container. And when those particles collide with the correct orientation, and when they collide with sufficient energy, then a reaction can occur. And we have also discussed the conditions for a chemical reaction to occur. Condition number one is that the kinetic energy must be greater than or equal to activation energy. And condition number two, they must collide with the correct orientation.